Our first session, as all of you know, was on relativity and issues of relativity, and of course, I think the NPA is best known for that issue, questioning Einstein and those kinds of things. But we are, I think, a pretty broad organization talking about a lot of things. But certainly, a related issue, directly related to issues of relativity, are issues related to light. That's going to be the topic of the next three presentations to finish out the morning. And our first talker in this, first speaker will be one we've had yesterday. Yesterday he spoke about gravity and his idea of dipoles accounting for the forces of gravity. And today he's going to be talking about those same mechanisms, dipole mechanisms, accounting for the speed of light as instantaneous forces acting at a distance. Dr. Ralph Sansbury.
I will try to show now that the speed of light, as measured, observed in terms of the time between the sending and receiving of light or radio signals, has to do with the time it takes for a relatively weak oscillation of charge at the receiver to become detectable. This delay time at the receiver can be calibrated to the source. What?
Mike, put the mic, there you go.
Oh, this.
Well, by your mouth.
Oh, by the mouth, closer. Okay. That had to be connected. Okay. This delay time at the receiver can be calibrated to the source-receiver distance by making the source weaker or the distance greater, so that the distance divided by the delay time is equal to the square root of the ratio of the electric to the magnetic constant. This is all a matter of calibration. In the GPS system, the microwave emitter-receiver calibration is made very precise. And in the reflected light beam apparati and distances chosen by Fizeau, Foucault, Michelson, etc., less precise. The lenses used by Bradley to measure stellar aberration produced a speed of light between the lenses about 8 feet or 12 feet apart, that was extrapolated to the unknown distance to the star being observed at times of year 6 months apart. By choosing a different objective lens for a given distance to the eyepiece, the speed between the lenses and by extrapolation of the star could be made closer to the speed of light. Let's see. Okay, so I'll go into more detail about exactly what happens there, but let me just then go for a moment to say that it helps to say that light is not something moving, but that it is rather this cumulative instantaneous force at a distance. It helps in a lot of ways. I mean, the Michelson-Morley Experiment of 1887 is very familiar, and if there was no movement of light, then the problems that have to be explained away by Einstein's theory of relativity and so on would not have occurred. So in the Michelson-Morley experiment, as you all know, the source of light was directed eastward in the direction of the Earth's spin at a speed v of the speed of the Earth to a half spinning speed to a half transparent slanted mirror, where half of the beam passed to a full mirror and half of the beam was reflected back. Let me put that, if I have that slide, just to, you all probably know it by heart, but okay, is that it? Okay, there it is. Oh, there it is. The back reflections of the beams on the slanted mirror were observed through a telescope at right angles, and so on, as you see, as you well know, and through a telescope at right angles to the longitudinal beam. It did not show the pattern of alternating dark and light bands that it should have showed if light was moving. But if light was at a constant speed c along each of these paths, it would have taken slightly longer for the light to move back and forth along the longitudinal path in the direction the Earth was moving than along the transverse path. So by comparing those two equations,
Use your mic.
by comparing those two equations, then you see the b squared over c squared. 1/2 of v squared over. I can't point at the same paper at the same time. Okay, so you just look at it, you see it. Okay. So the null result implied that one could not tell if time moved more slowly along the longitude. Let's see, Einstein's explanation for this lack of interference bands was, of course, that the time appeared to move slowly, more slowly, or distances only appeared to be less along the longitudinal round-trip path relative to distance or the passage of time along the transverse path, or vice versa. And that's my understanding of it. Maybe I should be corrected about that. The null result implied that one could not tell if time moved more slowly along the longitudinal scale or time moved more rapidly along the transverse scale. Only relative, not absolute measurements of space of time were possible, so there's no real way of clarifying that. But either explanation is possible. Well, is either explanation possible? I don't know. I think it's better to say light does not move. A simpler explanation is that light does not move, either as a wave or as moving particles called photons. Instead, light is the effect of cumulative instantaneous forces at a distance. Now, you need a mechanism for that, and I'm going to show later that the mechanism is Maxwell's wave theory, but involving transverse and longitudinal oscillating dipoles, not in space, but inside atomic nuclei, and that this process occurs over time. And it can take, milliseconds, or it can take hours. But anyway, let me go. I'll go to that just in a moment. The CERN neutrino result, showing that mass does not increase to infinity, at least according to the Lorentz factor at the speed of light, suggests that an alternative to the relativistic time dilation Lorentz factor explanation of the Michelson-Morley experiment is possible. That light speed measurements imply that light can be regarded as the cumulative effect of instantaneous forces at a distance. Weak microwave sources from 50 watts in the GPS system transmitter have longer delays than strong visible light sources from stars with more than 100 or 1,000 times the energy of our 10 to the 26 watt sun. The GPS delays are calibrated from Newtonian calculations of the distance between the satellites, about 12,000 miles from stationary receivers on the Earth, to be exactly equal to the assumed speed of light. The assumed speed of light is, as we know, the square root of the ratio of the magnetic constant of the electric constant. That's, but the strength of the signal can be calibrated so that this is so. And anyway, a small-scale test can be carried out to show light is indeed the cumulative effect of instantaneous forces at a distance. A 10 nanosecond light pulse from a laser can be blocked at a photocell 30 feet, 30 nanoseconds away at the expected time of arrival, and substantial light is still received on the photocell, as indicated by a voltage pulse above the noise level. When light is blocked from the photocell during the emission of the light pulse, but not at the expected time of arrival, negligible light is received. The CERN result showing that mass does not increase to infinity at the speed of light suggests that superluminal charged particles could exist inside atomic nuclei. Such orbital charges inside atomic nuclei can explain the apparent discrete atomic orbits and quantized wave energies associated with discrete radiation frequencies from heated gases, as in atomic spectra, and so on. That is, the outer atomic orbits must be in sync with the inner ones and with the orbital systems inside atomic nuclei. Radiation from these in-sync metastable radiation from these in-sync metastable orbits, the transition, anyway, there's no radiation from these in-sync metastable orbits or ground orbits. Why is there no radiation from these orbits? Because they dynamically adjust to one another, so they're out of phase. They help each other's movements and hinder each other's movements equally, and they cancel each other's radiation at a distance. But during a transition between these metastable ground states, there is no such time for adjustment, and the radiation is not canceled. You see it as the average of the frequencies of radiation associated with the metastable and ground orbits. Okay, no non-classical mechanics is needed. Only classical forces applied equally to subliminal and superluminal charged particles. Exchange interactions, quarks, the electroweak force, the strong force that are used to explain nuclear cohesion and the particle emissions from high-energy collisions involving electrons, protons, neutrons, helium ions, and so on, can be explained now in simpler, less abstract way, in terms not of energy exchanges between virtual particles over very small timescales, but in terms of electrical forces between actual charged particles, some 100 billion times smaller in mass and volume than the electron, moving at superluminal speeds between larger charged particles inside the nucleus and over similarly very small timescales. Light itself need not be mysteriously produced by instantaneous transitions between energy levels and then propagated as a wave or a photon or a probabilistic photon with a velocity equal to the speed of light. Instead, light or radiation in general may be regarded as the effect of oscillations of charged particles in a source that produce instantaneously at a distance in-phase oscillations of charged particles in the primary first receiver, first inside atomic nuclei, then after a delay, oscillations of electrons and free electrons or bound electrons, loosely bound electrons, with the widening of their orbits of the bound electrons leads to their ejection, as in a CCD camera. The required mechanism to produce such light transmission, similar to Maxwell's changing electric fields causing magnetic fields and changing magnetic fields causing electric fields, in Maxwell's theory, these effects propagate as a spherical wave in vacuous space. The photoelectric effect in 1901 showed quite clearly that the wave field energy was not large enough in the short time to produce the photoelectric effect that was observed in a matter of nanoseconds. It would have had to be at least, even in the case of resonant frequencies, a minute or so, so a billion times larger. So the Maxwell wave theory didn't work. The photon theory was finally accepted, I guess, by Einstein's idea many years later as the explanation for this transmission of light. Changing electric dipoles inside atomic nuclei are associated with radio and light radiation. Repeated oscillations of charge at a specific frequency in light or radio source produce increasing amplitudes of charge oscillations inside atomic nuclei in the parallel, say, longitudinal receiver before the amplitude of electric oscillations in a receiver is detectable. Accompanying the longitudinal oscillations are transverse oscillations that account for radiation pressure. I will describe, it's described in this book in the back. The mechanism, similar to Maxwell's field mechanism, but inside nuclei, is similar to Maxwell's field mechanism, but it's inside the nuclei. This and not a moving wave or particle would then account for the observed delays. For example, weak radio carrier oscillations, 1 billion per second, with phase shift modulation from a spacecraft 8-watt transmitter in the orbital path of Pluto, means 5 hours before the carrier and its phase shift modulations are detectable, so long as the receiver antenna is constantly turned to the direction of the spacecraft, which I'm assured it is by these contacts I had that were connected with the Pioneer case. Some of the reported in the desert over here in the Mojave. Some of the reported measurement anomalies and communication problems that they had may be traced to difficulties, the Pioneer anomaly for Pioneer 10, for example, in sustaining continuously open transmission and calibrating decreasing signal strength with increasing distance. But for distances more than 10 hours away in apparent communication with spacecraft at these distances, the delay might not be R over C, but it could be K R over C, K less than 1. That is, the R over C delay may apply for a specified number of repetitions of oscillating fields of a given strength, but that for greater strengths, or for a larger number and frequency of repetitions of even lesser strengths, the delay can be less. For example, Bradley's light speed measurement of the time it takes light from a distant star to be radiated from a telescope's objective lens to the eyepiece to the eye as the Earth moves at 29 kilometers per second under the observed star in the opposite direction, it moves 6 months earlier. Thus, the star appeared to be a few fraction of the degrees displaced from its 6 months earlier position. But this was attributable to a delay of a few nanoseconds between the objective lens and eyepiece, and the placement of the star moved. To extrapolate this delay or rate of speed from an 8-foot or 12-foot telescope to a star 10 to the 20 meters away is a bit of a stretch. But that is what Bradley did. His justification for doing it was that his speed of light estimate was then within 15% of Romer's estimate based on a completely different method 50 years earlier. And that method was questioned at the time by Cassini, who was the head of the observatory at Louis XIV's court in Paris, and he was really the reigning expert at the time. And it was conceivable that the difference of position of the Earth vis-a-vis the plane of the orbit of the moons of Jupiter and the orbit of Jupiter, very slight differences in angle, but over such large distances, would make it, the visibility of these moons change when the Earth is, say, closer and it's visible, and further away and it's still visible. So anyway, the absolute magnitude of the star he was observing, Gamma Draconis, in the Dragon constellation, we now know is plus 4.8, while the Sun is minus 1.93. A difference of minus 6.73 implies the star is as bright as 700 suns. The Sun at 3.9 times 10 to the 26 watts, or 10 to the 2400 watt light bulbs, is pretty bright, and that's even much brighter. So it's conceivable that that very bright star can be this very faint point of light in the sky, and it can then be observed just within a few nanoseconds after it hits the objective lens and then comes to the telescope, and that would explain completely Bradley's stellar aberration phenomenon. The other extreme is the delay of weak radio signals from spacecraft near Pluto, I guess I mentioned before, not near Pluto, but near Pluto's orbit, which could be 5 hours away, while the delay of much greater power light sources like stars could be just nanoseconds. Okay, now, the Maxwell delay mechanism to explain how this delay occurs inside the nucleus is based on the understanding that the magnetic force between parallel current-carrying wires is produced by collinear electrostatic dipoles inside the lattice nuclei, in turn produced by sustained electric fields perpendicular to the electric dipole fields in each of the parallel wires. So I talked about this in the gravity talk, and I can review a little bit of it now. And that leads to this mechanism. That is, changing longitudinal fields changing longitudinal fields of the source produce a longitudinal field in the receiver. If you think of a radio antenna and a wire, tall vertical wire, and another vertical wire as a receiver, and then transverse dipole fields are produced as this current moves due to the electric fields at the receiver antenna. And these transverse dipole fields in turn produce, as they change, longitudinal dipole fields that are opposite to this, opposite to the original longitudinal field direction. And this goes back and forth, back and forth, back and forth for milliseconds or 5 hours. And gradually you get an increase more and more of the amplitude of oscillation of charge inside the nucleus, and that carries over at some point to the loosely bound electrons in a silicon photodiode, or in whatever the free electrons, and they become a detectable signal of light. Okay, now if everybody here has seen this thing about how electric dipoles are produced. 10 minutes? Oh, okay. So let me review again how electric dipoles are produced inside a current-carrying wire, and this would apply to an antenna or a photocell, but I'm going to consider an example of parallel current-carrying wires first, and then apply it to alternating currents in radio antenna and light sources and receivers. Okay, so now let me get to the slides that were used in the to show this. Okay, let's see. Okay, all right. So this shows the forces between electric dipoles. Parallel electric dipoles repel each other, collinear in the same direction, attract, collinear in the opposite direction, repel twice as strongly as the parallel dipoles attract. So this you have to sort of keep in mind. And collinear dipoles, if they're in the opposite direction, will repel. And I think a lot of these things I've seen in the Tesla conference of magnetic levitation and railguns and so forth have to do with producing oppositely oriented electric dipoles in the in not just the atomic nuclei, but mainly in probably in magnetic materials in the orbits of iron, cobalt, and nickel, and so on, that produce, anyway, these can produce repelling forces, and so magnets can repel each other very strongly and produce dramatic effects. But since everything participates in the electric dipoles in the Earth, caused by the orbital and spinning motion of the Earth, they can't really overcome that. I mean, they're on top of. I mean, they can overcome that, but that still is there. So they're overcoming this basic downward gravitational force. All right. Anyway, I'm getting distracted. All right. So now let's see. The second slide shows how these dipoles are created in atomic nuclei and free electrons. I assume that the atomic nucleus, like of copper, what is copper? It's 29. Is really 30. Has a charge of plus 30 and an orbital charge of minus e. Plus 30 e, an orbital charge of minus e. Net charge 29 e. And this orbital charge of minus e is a very small particle. Moving it will turn out very superluminal velocity, and this can be produced. Electric field acting on this can produce an ellipse, and a change in the average, change in the distance between the center of negative charge and the center of positive charge, which then produces a dipole. And how does that ellipse occur? Well, this diagram on the right shows how the ellipse occurs when transverse to the field producing an elliptical extension of a circular orbit. Okay, now we can equate the attraction of 2 millimeter diameter, 10 to the minus 6 square millimeter copper wires, 2 centimeters apart, with a density of 10 to the 28 carrying currents of 1 amp, which is equal to 10 to the 28 times 10 to the minus 6 times 10 to the minus 19 times VE, which we don't know yet. And this will produce an attraction of collinear electric dipoles ER V over C. So we multiply R times V over C and we get an electric dipole. Now, why do we do that? Well, when you have two wires with the collinear electric dipoles near each other, the electric dipole, transverse electric dipole field will interfere with the production of the electric dipole field in the other wire. Okay, so since we can do that, we then get the equation 10 to the minus 7 II ds prime over r squared, the familiar Ampere equation for the magnetic force between short current segments of wire. And that is equal then to this. We set this equal, and then we have to find out what happens. Well, the r's in the numerator cancel with the r fourth in the denominator. We get an r squared force, and we're left with this expression, and we can solve then for V sub e, which is about 10 to the minus 5, 10 to the minus 5 meters per second. Okay, so, and then from this, we can calculate what E is necessary to produce this velocity, and then we can see what sort of ellipse this E could produce on the atomic nuclei. And the ellipse will have, this is the value for the ellipse, the eccentricity over 1 minus the eccentricity times the circular radius, and that must be equal to our RV E sub E over C. Now, notice this elliptical extension in the nucleus can't exceed the inner shell of electrons, which is 10 to the minus 11 about, 10 to the minus 11 about. So there's just a small room for these dipoles to exist. They have to be smaller than the 10 to the minus 15 radius nucleus, and they can't be any bigger than 10 to the minus 11. I mean, it's a pretty big range, but it's still a very small number. But in this case, for this magnetic force between these two current carrying wires carrying 1 amp, a few newtons force, it's produced by all of these electric dipoles if they are 1.57 times 10 to the minus 15 meters in the billions of atomic lattice nuclei in each of the wires. Okay, so knowing this, we can then go on to solve for what is the mass of this particle that will allow this to happen. Well, the central force on this orbiting particle is about 10 squared newtons, and this force from the electric field is about 10 to the minus 22 newtons. So that this mass has to be very small. And if we solve this equation, we see it's 10 to the minus 55. So this is the most important thing. And from this, from these basics, we can derive this mechanism for we can derive the force for, we can derive Maxwell's equations taking place entirely inside the nucleus. You think, well, okay, that nucleus is too small for any of this to happen. But you just have to remember that this particle probably is the size, if it's the same, if the volume is the same as the mass in magnitude, you have 100 billion times smaller than the electron in volume and mass. So you have a huge area, volume, inside this nucleus relative to the size of these particles and the charge. And then you have these huge speeds. So in this situation, it is possible then for transverse electric dipoles, changing transverse electric dipoles inside the nucleus to produce longitudinal dipoles, and changing longitudinal dipoles to produce changing transverse dipoles, and this gradual increase is happening then in the nucleus. So you don't run into any of the problems of Maxwell's theory that energy is lost in space and cannot account for the photoelectric effect. Okay. All right. So I can't go into the Maxwell, to the mathematics of the Maxwell details theory, but they follow from this, the idea I've told you about, and you can read this, and I have a book coming out at Amazon in a couple of weeks called Faster Than Light, which has all of the mathematics of this and much more. So anyway, are there any questions?
We don't have time for a lot of questions because we're getting late. But you know, Ralph, I think you're the only person that I know, at least, who I agree with regarding instantaneous action at a distance. I'd say the vast majority of people, probably even in this room, say that's impossible. You can't have instantaneous forces at a distance.
Right.
The way I conceive of it is there's nothing moving at an infinite speed.
Right.
Nothing moves. All we're talking about is relative rotation of or motion of these things going on inside the atom.
Yes.
And that is what light is. Is that what you're saying?
That's what I'm saying.
That's exactly what I've been
Yes.
saying for 3 years too. So.
Oh, wonderful.
Hallelujah.
Wonderful. Okay. All right.
All right, one more?
Yes.
Well, okay.
I just kind of wonder if it's my understanding that a few pages from the end of Maxwell's treatise on electricity and magnetism, that Maxwell discusses what seems to me to be dipole action, according to Professor Betty in Italy, and Maxwell seems to claim that his equations, as well as a lot more, seems to be consistent with Professor Betty's idea of oscillating dipoles, and I just wondered, first of all, if you have any comments.
Well, I'm not talking so much about oscillating. I'm not talking about a field of movement of oscillating dipoles. I mean, the oscillation of the longitudinal field and the transverse field. I mean, this is an oscillation of amplitude, charges, and the amplitude builds up, and after a while it becomes strong enough so it's detectable. But the forces initially are instantaneous if they're strong enough, and they will build up. And they will build up if they are strong enough. If they're not strong enough, you won't get a buildup of oscillating charge. And I mean, the dipoles really have to do with the polarization inside the atomic nuclei during this process, the transverse and there's momentary dipoles, and that accounts then for the light pressure.
And do you regard, kind of an ether is kind of necessary to your paradigm?
No, that's the nice thing about it. You don't need an ether. You don't need a medium. You don't need a photon. You don't need to get into all the problems with probabilistic photons. Everything is instantaneous, and if things are too far away, it won't work. But if they're close enough, the magnitude of oscillation of charge will increase beyond noise, and you have a detectable signal. It's as simple as that. Everything is much simpler. Okay.